Okay, good afternoon to everybody. Welcome to this 7th seminar within the DUCE Colloquia. Today we have the pleasure to have a speaker, Professor Karen Rudie. Thank you very much for being with us today, Karen. And let me spend a few words about Karen. So she is actually a professor at Queen's University, Canada, in the Department of Electrical and Computer Engineering and the School of Computing. She obtained her PhD in 1992 from the University of Toronto in the Systems Control Group under the supervision of Professor Wonham. In 1992-1993, she was a postdoctoral researcher at the Institute for Mathematics and its Application in Minnesota. From 2004-2006, she was an IEEE Control System Society Distinguished Lecturer. She had a very strong editorial activities. In fact, she was involved in the editorial board of several prestigious journals, such as Journal of Discrete-Event Dynamic Systems, IEEE Transactions on Control Systems Technology, IEEE Transactions on Automatic Control, and also IEEE Control Systems Magazine. She is actually a fellow of the IEEE. Her main research interests include control of discrete event systems. Thanks again for being with us today. Karen, please, you can share the screen and start.
I will. Thank you so much for inviting me. I'm really honored to be invited. Okay. Are you able to see the screen now?
Yes.
Okay, good. So I think, and you can see my so-called laser pointer moving?
Yes.
Okay, perfect. Thank you so much. So my talk is going to be about how to use discrete event systems to keep secrets secret. And I'm from Queens in electrical and computer engineering, and I'm also affiliated with a lab there called Ingenuity Labs Research Institute. So why should we worry about security, and what role can discrete event systems play? So first of all, in much of our day-to-day current life and really very near future life, there are a lot of security concerns. So if we look at, imagine self-driving cars, which isn't really all that far away, and a good thing because I hate driving. We have, sorry, I'm talking now really about systems that have also some form of communication. So if we look at banking systems, you put your bank card in, you give your password. Obviously, if somebody gets your password, that's a big problem. We have smart homes now, and that's really current. It's not even a future world. And smart cities, which are emerging. So microgrids, power grids, electrical distribution that's becoming more decentralized and more interconnected to networks. And as soon as you have systems like that, where you need some kind of communication, so for self-driving cars to manage, they obviously have to have some kind of communication. So if some car is changing lane, there needs to be some kind of communication between that, let's say, and a car near it. But as soon as you have communication, you also have the possibility of some basically nefarious agent listening in and causing damage. And what kind of damage can, basically a bad guy do? Well, for something like self-driving cars, even a single event like put on the brakes when you don't intend to put on the brakes could be completely disastrous. And in a smart home or a smart business where something like the temperature might be controlled of the room, or your oven can be turned on, you could obviously cause massive damage to an industry if you had, you turned the temperature up to some crazy number. You could burn down a building, for example. And why discrete event systems? So the kinds of problems I've just described, as I said, havoc can be caused even by a single event being altered. So as I said, in self-driving cars, the event could be, accelerate or put on your brakes. So let me tell you a bit first. What I'm going to do in this talk is talk about discrete event systems, how we model them, what the issues are, and then I'll get into security. So for some of you who are not in discrete event systems, but familiar with control systems, we think of our systems that we're going to control in a similar way to the standard feedback loop. You have a plant and a controller, and in discrete event systems, the controller is often called a supervisor. And you imagine that the plant in this case is not a collection of transfer functions or something like that. It's a generator of sequences of events. So let's look at this sequence here. Imagine that A, B, C, D, these are events that can happen. So this string or sequence of events says A happens once, then B again, then C, and so on. And the idea is that we imagine that some of those events can be turned on or off, so enabled or disabled, and we call those controllable events, and others cannot be disabled, and we call them uncontrollable. And the idea is that a controller will see a sequence of events that happened and make a decision about what events should now be disabled. So after string S, we might say that what should be allowed to happen is events A or E. But on the other hand, if a different sequence of events happened, we might say that what can be allowed to happen is A, so E cannot happen. By the way, you're all seeing this fine, right? Because I can't see what's on your screen.
Yeah.
Okay.
Yeah, it's fine.
All right. Okay. So the other thing going on for many discrete event systems is that they might just be partially observed. So what that means is that if a sequence S is generated, that may not be what the controller sees. So we can imagine that really what the controller sees is some filtered version of that. We call that a projection, P of S. So again, let's suppose that's the sequence of events that happens. Maybe the controller doesn't see the event occurrences B and C, so it only sees A, D, D, D. And it still has to make a decision about, what should be allowed to happen. Okay, so we have that set up, and as I said, we want to talk about adversaries. So we want to talk about security issues when you have sequences of events that are occurring. So what kinds of security are we talking about? So first of all, the distinguishing will be in what the adversary can or can't do. So the first thing is we can imagine an adversary that doesn't really change anything. It just observes events. So we have, again, the same setup. The supervisor observes some filtered version of the sequence of events, but the adversary observes some other sequence. It might or might not be the same. And the adversary knows, therefore, something about what's going on. And in that setting, we are interested in a feature that we call opacity. I'm going to be discussing that in a lot of detail in this talk. And a further property of partially observed systems in terms of security is whether or not the adversary is supervisor aware. And again, when I go through the example I'm going to do, I'll discuss that. But that essentially means, how smart is the adversary? And ideally, you want to design your systems for a smart adversary, because obviously if the adversary is stupid, that just makes it, in some sense, easier for you. So in addition to adversaries that can just observe, a more powerful adversary is one that can actually alter the event occurrences. And those would fall under the category of something called attack models. And again, and what you have there is that different kinds of things can be attacked. So an adversary could attack plant outputs. So that means it could, for example, mess with the sensors, alter the sensors so that the reading the supervisor thinks it's seeing is not really what happened in the plant. And it could also alter the actuator outputs so that the supervisor makes a decision, but that decision isn't what's actually implemented on the plant. And also, again, the adversary may or may not be supervisor aware. So the key approaches to security and discrete event systems that I'm going to talk about in this talk are twofold. The first is opacity. And opacity is the ability of a system to ensure that a secret state or states or secret event sequences cannot be distinguished from non-secret ones. And the other thing we'll look at is attack models. So attacks on sensors or actuators, where events or actions are inserted or removed or altered by a hostile agent. And as I said, when it's on the sensor outputs, the supervisor thinks a different event sequence happened than really did happen. And when it's on the actuator outputs, the system does different actions than the supervisor intended. I'm going to have a running example throughout this talk, and it's motivated by an industrial project that I worked on with a bunch of other professors and students, and the principal investigator is Josh Marshall in my department. And it's a project with General Dynamics Land Systems and Defense Research and Development Canada, and you'll see from the example why this would be of interest to defense organizations. So let's imagine we have some sort of terrain, and in the terrain there's clearings. So there's sort of bodies of land where there may or may not be, soldiers. And let's imagine that there's going to be an autonomous vehicle moving along this land. So from clearing to clearing. So these are the ways it can move. So first of all, we can model that with the discrete event systems. So this little arrow going in stands for the initial state. That's where we imagine that our autonomous vehicle starts. And we're going to label each of the clearings with a number. So if the autonomous vehicle travels from this clearing to this one, it's traveling from clearing 1 to clearing 2. And the arrows indicate the direction in which the vehicle can travel. And, so in discrete event systems, you notice, and this is like just like a graph in graph theory, a directed graph. So you notice here that we can go from 3 to 6, but not 6 to 3. On the other hand, between 2 and 3, we can go in both directions. So if you're thinking of, let's say, in this real problem, the vehicle, you could imagine a vehicle is maybe climbing, maybe it's going over some terrain that's very slippery or hilly, so it can only go in one direction and not the other, or maybe, it can go down something, but it can't go back up. So that's a way you can imagine the direction might be both ways or one. So also in discrete event systems, we usually have distinguished states. So you notice the ones that are in gray here, that in a standard discrete event system might stand for, completing a particular sequence of events or completing a mission or something. In the case of security, we're going to use those distinguished states to stand for some sort of secret. So for example, we could imagine that 10, 11, and 13 are spots where there might be a fallen soldier or someone in need of rescue, and we want to keep that location secret, perhaps. So now I just kind of moved away the image of the terrain, and this is a discrete event system. And as you can see, what I've also done here is I've now labeled the edges so that I can talk about the event going from 6 to 7, which would be called a transition. We'll just label that C67, so going from clearing 6 to 7. And this is a deterministic finite automaton. Deterministic because at any given state, so if I look at state 5, I might have 2 transitions coming out of it, but those 2 are different transitions. So in other words, if C58 happens, it is 100% determined that you will land in state 8. And I'm going to distinguish that from something we'll look at later called a non-deterministic automaton. Okay, and on this automaton, we also have controllable events and uncontrollable ones. So the controllable ones are indicated with a little, you see this little, might be hard to see, but this little stripe through it. And that means it's some event I can prevent from happening. But on the other hand, if you look down here at this event, it has no strike, so I can't stop it from happening. So in the autonomous vehicle setting, what we can imagine is, let's say you are in clearing 9. Let's imagine that it's very slippery, and the minute you get to clearing 9, the vehicle will uncontrollably slide down to clearing 13. So you can't stop it from sliding down. If we were talking about vehicles on a road, you could think of controllable events as being places where there are, for example, stoplights. You could make the car stop there, and uncontrollable ones would be ones where once it reaches that intersection, you can't stop it from going through because, let's say, there's no light. Okay, so now how do uncontrollable events impact things? So let's imagine that the sequence of events from clearing 1 to 12 to 8 is good. That's a good sequence. But we want to stop the vehicle from going to clearing 5. So this sequence here is good, but after that, it's bad. So no problem. We would be able to just disable C85. On the other hand, if this sequence was good, but this part is bad, we couldn't stop it because, as I said, we can't stop an uncontrollable event. So that's kind of what gives rise to the earliest work in the field, which was a field started by Murray Wanham and Peter Ramage in the early 1980s. And the idea is that you turn on and off controllable events to ensure that only good sequences of events happen. But as I said, you can't always make sure that only good things happen and none of the bad stuff happens. So one of the key results in the field is trying to ensure that the largest set of good behavior happens. And that was kind of the key results early on in the field, producing a unique, minimally restrictive supervisor, a supervisor that lets as many good things happen as possible and nothing bad. And that can be produced in polynomial time. And we'll see that's in contrast to a lot of the negative computational complexity results in partial observation. All right, so let's go back to our motivating problem. And now imagine that we're actually going to have partial observation. And here's how it's going to come about. So let's imagine that the clearings are grouped into regions. So all these 3 clearings are region 1, these 4 clearings are region 2, and so on. And the idea is going to be that as the vehicle travels around, it's going to send communications maybe to another vehicle, indicating when it moves to a different region. And maybe it does that because there might be multiple vehicles searching this terrain, and you want them to be efficient. Like if I'm searching region 2, you shouldn't be searching region 2. You may as well search another region. So the vehicles are going to communicate when they move from one region to another. Okay, and those communicate. So again, we'll put our deterministic automaton or a finite state machine overlaid on this. And now what we're going to do is just communicate when we move regions. So we're going to label the communication with the region we're heading into. So when we go from clearing 3 to 6, we are heading into region 2. When we go from clearing 7 to clearing 10, we're heading into region 3. So if the vehicle we're traveling around, so when it goes from 1 to 2 to 3, it doesn't emit any communication, but as soon as it goes here, it says R2. Okay, and the idea is going to be that the only events that are observed are going to be those ones that are communicated. Okay, so we communicate when we're going into a region, and I've put dotted lines on the transitions that are not communicated. So effectively, we're going to imagine now the following situation. So first of all, if I'm a vehicle traveling and I communicate to, let's say, another vehicle that's part of my team, then they will see those communications, those events, but so will an adversary. So if some hostile agent is listening in and trying to figure out where I'm going, then that hostile agent will also hear, for example, if I go from 1 to 2 to 3 to 6 to 7 to 10, then what my teammate and what a hostile agent will hear is R2, R3. Okay? So, and again, let's imagine that 10, 11, and 13 are secret states. Maybe they're spots that I don't want a hostile agent to know if I'm in any of those states. Okay, so what happens when a supervisor, now a controller, only sees some events? So let's suppose this vehicle travels from 1 to 2 to 4. So that means the only event seen in that sequence is R2. But it's also the case if the vehicle continues to 5. So if the path is 1, 2, 4, 5, still it will be the case that just R2 is heard. And also it will be the case that R2 is heard if I go on this path here or on this path here. So I see that if the only event seen is R2, you would not know if the vehicle is in state 4, 5, 6, or 7. Okay? Also, I want you to notice that when I start off, if the vehicle's traveling anywhere between 1, 2, 3, nothing is seen. So before any event is seen at all, the vehicle really could be in state 1, 2, or 3. So there's a way to actually capture this in a structure that kind of holds that information. So on the bottom left, I just have the diagram I had on the previous slide. And what I have up here is a structure that we call an observer that essentially captures what an observing agent would see. So as we said, initially the vehicle could be in any of states 1, 2, or 3. As soon as R2 is seen, it could be in any of 4, 5, 6, or 7, and so on. And then this structure captures all those possibilities. Okay, so partial observation is bad and good. So it's bad because a unique, minimally restrictive supervisor is no longer possible since there may be many incomparable solutions. And I haven't really shown you why that's the case, but I maybe gave you a taste of it since you don't really know where the vehicle could be. It could be in state 3, 4, 5, 6, or 7. If you're trying to control it, control is harder because you have to consider multiple possible sequences. And in fact, it becomes an exponential problem. On the other hand, even though control is harder, keeping information hidden is easier because you're not seeing every event. So you can judiciously hide information so that an adversary doesn't know enough about what's going on. So in that sense, for many, many years, for decades, partial observation in discrete event systems was problematic. But when it comes to security problems, it's actually, as I put it on the top, it's your friend. Okay, so let's go now and talk about opacity. So again, just to remind you, opacity is the ability of a system to ensure that some secret can't be distinguished from a non-secret. And I want to say I've put some slides at the end that I can throw up only if there's extra time that gives more of the kind of thing you would have in a paper that says who did what in the field. I'm not putting that up here to not just take time away, but I don't want you to think like I am not one of the original, inventors of opacity. I'm not even one of the big players in the field. So I'm, as I said, I'm not listing off all the people at this point. So I just put a couple of things here that in computer science, I believe this was first looked at in 2004. Then it was tailored to transition systems in 2008. And it's become a very hot topic in discrete event systems, after that, or even around that time. And so we'll say that a system is opaque if a string that is secret or leads to a secret state looks like another string in the system that is non-secret. And I want to say there's different notions of opacity. Again, if there's extra time, I can go into that at the end, such as whether or not that one's every secret is confusable or just one secret. But we're not going to focus it on that right now. Right now, we're going to say it's opaque if any string that is secret could be confused if all strings that are secret can be confused with non-secret ones. So let's look at an example of when it's opaque and when it's not opaque. So let's suppose that state 12 was the only secret state in that diagram. So when we convert that diagram again to our observer, we see here that if you look on here, the only time 12 appears in the observer is when it's confusable with 13. So when the system is actually at state 12, an observing agent thinks it could be at 12 or 13. 12 is gray, meaning it's secret. 13 is not secret. So that's good. It means we never know for sure if we're in a secret state, because anytime the system is in a secret state, we also think it could be in a non-secret state. So it's opaque. But here's an example when it's not opaque. So if we have 10, 11, and 13, which was our original setup, being secret, and we do the same conversion, the structure's the same. The difference here is that although if the system is at state 13, which is secret, an observing agent thinks it could be at 12, so it'll be confused. And similarly here, if in fact the system is at state 13, an adversary can know it's at 13. So we see that 13 is in a fully gray state. So the only estimate in that circle of the observer is one where it's secret. So if a path where's the path? Goes here, 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 then if that occurs, R2, R3, R4U, it will know that in fact the agent is in a secret state. By the way, I apologize. I forgot to point out on the original diagram when the transition is uncontrollable, I put a little U after it. So R4U means it goes uncontrollably into region 4. Okay, so if a system is not opaque, you would ideally want to make it opaque. So an obvious thing to do would be to hide more events, right? Since the more you hide, the less you see, hence the more the system is opaque. Why not just do that? So that might be because it might not be possible. Maybe the particular event is one you cannot stop from being seen. Or maybe you want transparency for a particular reason, like I'm thinking there more at an industrial setting where you want certain things to be seen, say, by the public. Or in the case of like the autonomous vehicles, maybe you have multiple agents and they need to give information to each other. So in that example I have, they're transmitting information to each other to help each other navigate the terrain. So it's not possible to just hide information. So another strategy, if you can't hide information, is to enforce opacity through control. And opacity enforcement problems have been studied. Again, I was not one of the original people that started looking at this, but they differ in what kind of opacity is enforced. So as I said, whether you want to just ensure that a single secret is not revealed or all secrets are not revealed or various other things. What capabilities are assumed for the observing agent? So does it see everything the supervisor sees? Is the solution minimally restrictive? Does it only disable stuff that has to be disabled? And whether the adversary is supervisor aware. And again, this talk is not intended to be comprehensive in terms of really paying homage to all the people in the field who have worked on this. What I list here are the people who've done opacity enforcement problems that have most strongly informed the work that I'm going to present to you. So for control to ensure opacity, this is the setup I'm going to use in the research that we were doing on this. So first of all, we're going to assume that the events that can be seen by a supervisor are fixed, and those seen by an adversary are fixed, and they don't have to be the same. So you can't choose what you hide or reveal, because what is revealed to the adversary is not under your control. You can only stop events from happening so that the controlled system is opaque. And you want to do this by disabling as little as possible to guarantee a minimally restrictive solution. We will also assume that the adversary is supervisor aware. And this is work I worked on with some of my students, former postdoc, and a visiting researcher. And it's been in the pipeline in JDEDS for 2 years. So I'm hoping it'll appear soon. I should have also said at the beginning of this talk, and maybe it's crazy because you're recording it, I'm speaking about work that has not, some of it that has not been published, but I thought it was more fun to talk about my current work than some of the other work. So it's maybe a bit risky. Okay, so I'm going to just show you on an example how our strategy works. So taking that same problem of the vehicle, we create a composite structure where the number on top indicates the state that the vehicle is in. So this part here, like it goes from clearing 1 to clearing 12 to clearing 8. Then the thing on the bottom is what the observer sees. So I just combined the plant and the observer in a composite structure. And it's really almost the same as something called the augmented eye observer that Alessandro Gua and other researchers, Tong, it comes from the paper by Tong and colleagues. So I create that structure, okay? Now, let's, okay. So as we see here, as I pointed out when we were talking about the problem that isn't opaque, if the system goes through this sequence, so the sequence in blue, it lands at state 13, and the adversary knows it's in state 13, and the gray states are secret states. So this would make the system not opaque. So we most surely have to ensure that any transitions coming into clearing 13 are disabled. But if you notice, the ones coming into clearing 13 in red are uncontrollable. We can't stop them from happening. So we're going to have to stop the vehicle from even getting into the states from which we can get to clearing 13. So if you see here, we really can't go into clearing 9 because from there we go to clearing 13 uncontrollably. Okay, so we're going to have to prevent those things from happening. So we do that. We basically disable those events, which means we don't get into those states, and in turn, we don't get into those clearings. Okay, so if we see here, that makes certain states no longer reachable. So I'm hoping you can see on your screen, for example, 8 and 9, clearings 8 and 9 are no longer reachable. We've whited them out. So look here at this state here. Before we did anything, when the vehicle is in clearing 10, an adversary thinks it could be in 8, 9, 10, or 11. But remember, I told you the adversary is supervisor aware. So that means if 8 and 9 are no longer accessible, like the vehicle will never get to clearings 8 or 9, in fact, we need to update the adversary's view, because the adversary is not going to think that 8 and 9 are options. So when we update it, we see that the adversary will only think it's really in states 10 or 11. But now we have to iterate, because now this originally, so let me go back here. Originally, when the vehicle's in state 10, the adversary thinks it's in 8, 9, 10, or 11. 10 and 11 are secret, 8 and 9 are, so the adversary would not know if it's in a secret state. But once we prevent the vehicle from traveling to clearings 8 and 9, the adversary would know if the vehicle reaches either state 10 or 11, that it's in one of 10 or 11, and both of those are secret, so it would know that the vehicle's in a secret state. So we have to repeat, we have to get rid of those states and anything coming into them. And we do that, And now we see that what we end up with is an object where any of the states that have gray also have white. So if the vehicle is in either state 12 or 13, the adversary doesn't know if it's in 12 or 13, so it will not know if it's in a secret state. Okay, so through control, we have ensured that the final system will be opaque. So we could take this object and effectively, this is our supervisor. It says when you are in state 1, you can go here, but it disables the events coming out. So we could hook it up to our plant and disable the relevant events so that we can't go to state 8 or 9 and so on. But notice that that also means that if, for example, there was a fallen soldier in clearing 8 or 9, our vehicle that is searching for that soldier will never get there. So it's true that an adversary won't know if we're in clearing 8 or 9, but we're never even going to get to clearing 8 or 9. So we see right now that one of the problems with using control to ensure opacity is that you also limit the behavior of the system, and that may not be adequate. Oops, sorry. Sorry, I'm having a problem. Okay, there we go. So before I kind of finish off the section on opacity, I want to say that with another student of mine who's now doing a PhD, but this was her master's work, we applied opacity to that problem with the industry problem that I've been working on. And the real problem we're working on is a little more complicated than what I showed you so far. So what we really have is we imagine that there's actually a cost to going from clearing to clearing, and we'll call that a traversability cost. And that cost could be distance, like it could be that from this clearing to this one, it's 20 kilometers, and from this to this, it's 15 kilometers. Or the cost could be a measure of how hard it is to traverse that terrain. It could be that going from here to here, it's very uphill. I have to use a lot of resources, but this is flat land, or whatever. It's some measure of difficulty. And furthermore, we're going to assume that there's some fallen soldier in one of these clearings, but we don't know where. So we can't use standard opacity because there is no single state or states that are secret. Any particular state could be secret. We want to have an adversary not know when we're in, a secret state. But we want to extend opacity to a non-binary measure. So it's not just that the system is opaque or not opaque. Sorry, let me go back to this. So for example, let's suppose there was, a fallen soldier here. We don't want it just to be that, this clearing is confusable with one other. We want to be able to speak about how confused is an adversary. So for example, if this clearing is confusable with 6 other clearings, as opposed to just one other, that would be worse for an adversary because it would have to search 6 different clearings to figure out where the fallen soldier is. So clearly we need for opacity to adjust the definition so that we can talk about how confused an adversary is. And so Bryony introduced the notion of degree of opacity, and it measures how confused an adversary is and not just whether they're confused. And it can be measured by any monotonic function of the system properties. So we, for example, in the real problem we did, we just we could count the number of states that are confused. We could count the distance to some state. In the example we did, we have a function that captures the time it takes to search a group of clearings. And so in our case, the opacity enforcement is we wanted to prescribe a degree of opacity. So for example, if an adversary can search the clearings in less than 30 seconds, 30 minutes, that would be a problem because we know that they're going to send out their vehicle if it only takes them 30 minutes to search. So we want to do opacity enforcement to ensure that wherever the vehicle is, it would take the adversary too long to search it. So that's the measure we used. Okay. So with and I should say that's a paper also we've submitted to, I hesitate to say this in case it's not accepted, but we submitted it to CDC. So what are the issues with opacity? Well, building observers is an exponential time operation, because if you have n states in the plant, since the observer states are subsets of those original states, you could have 2 to the n states in the observer. Using control to ensure opacity can overly restrict the system behavior. And also, it may not be enough to just hide or control the system, especially if an adversary can erase or insert or alter events. So that's the next section I'm going to talk about, is attack models. So Giordano, I think we started late. Am I okay to go past the time? Because this section is...
No, Karen. Indeed, you have 1 hour, so you can go ahead with this.
Okay, good. All right, I won't use up more than an hour. So let me go back again now to discuss attack models. So in attack models, we're going to look at, again, the adversary can delete or insert events at sensors or actuators, and it may or may not be supervisor aware. So let's suppose the sequence of events A, B, B, C, D, D, E, F is generated, and we have an adversary that erases the second B and adds a third D. Then that's what the sequence is going to look like to the controller. So this is the sequence that actually happened, but this is the sequence that the controller sees. And so considerations that you can make when you're modeling attacks, again, what are the capabilities of the adversary? Can the attack just be detected? Can it be mitigated? Can it be prevented? And can we control the system so that a supervisor can ensure that good behavior happens even in the face of an attack? So what I'm going to talk about is a very specific model that was appeared in the literature in 2018 by Wakeki and colleagues. And then some research I did with Patricia Pena in Brazil and our student Michelle on to extend that model. So the model you have here is a plant, and you have multiple attackers, each of which can attack some events from sensors. So it's only sensor attacks. But the problem is, even though only one attacker can attack at once, we don't know which attacker is the one that's going to attack. And we're going to assume that attackers may delete or insert events. So in the face of an unknown sensor attack, under what conditions can a supervisor enforce some desired behavior? Namely, we want the supervisor to make sure that good sequences happen and bad sequences don't happen. And the result that they came up with was that the system must satisfy a property called p-observability for an attack set. I'm not putting up the mathematics of that, don't worry about it. The informal description is if 2 event sequences look the same to a supervisor, even if an attack has happened, so remember, what the supervisors see may not really be what happened, then the sequences can't lead to control inconsistent states. And control inconsistent means a state where different control decisions would be required. So I'm gonna talk to you now and show you an example. And this is research. Oops, I don't seem to have that on my screen. This is research with Patricia and Michelle. So let's imagine that you have, like maybe this is just a process in a manufacturing plant, and N is a new part arrives. You're at state zero, a new part arrives. You don't know, that part could be part A or part B. And whichever part it is, we test the part and either it passes the test or it fails. If it passes, we put the part on a conveyor belt, and if it fails, then we discard it. Okay? So notice that at state 3, I want to be allowed to put the part on a conveyor belt. This part here, this CD with the dotted line, it's not really part of the diagram. It's just to indicate that at state 0, there is no event C or D coming out. So if the part has not yet been tested, I don't want to put it on a conveyor belt yet, nor discard it, because I don't know what it is. So states 0 and 3 are control inconsistent, because at 3, I want to enable event C, and at state 0, I want to disable it. Now let's imagine I have 2 attackers. Attacker 1 can attack events A and N, and attacker 2 can attack events F, P, and B. So let's imagine that the supervisor sees the event sequence NA. Well, that might or might not be what really happened in the plant. So it could be that, in fact, nothing happened in the plant, and attacker 1 inserted an N and an A, because it can insert events N and A or delete them. So a supervisor thinks NA has happened, but actually nothing has happened. By the way, in discrete event systems, we use that epsilon symbol to indicate a sequence of nothingness. So nothing has happened yet. On the other hand, it also could be that NAP happened and attacker 2 deleted the P. And so that's why I see NA. So notice that I see NA. It could be nothing happened, the system is really here, or it could be NAP happened, the system is here. And as I said earlier, those 2 states are control inconsistent. So so in this particular problem, with these possible attackers, the system would not be P observable. We cannot, in fact, control the system because we cannot make a decision about whether to enable event C, since we might not know if we're at state 0 or 3 when an attack happens. So the work that we looked at, which is in a JDEDS paper in 2021, is that how can we found a way to visualize the P observability property to determine if there's an attack or not. So let's look here at attacker 1. So first of all, let me say what we do, and again, I'm not going to really show you the mathematics of it. If it really interests you, you could read the paper, but I'm going to just try to give you a feel for it. So Michelle created a relation that's going to capture pairs of states being related when essentially they look the same under attack. So let's look here at the green or dotted lines surrounding states. So that indicates, if you look here, since attacker 1 can insert an N, state 0 and states 1 are indistinguishable because I could be at state 0 and the attacker inserts an N, or I could be at state 1 and the attacker has deleted an N. And similarly, 1 and 2 can be confusable to a supervisor because the attacker can insert or delete an A. We do the same thing with attacker 2. So the longer dashed lines, and if you're able to see color, the blue, pulls together pairs of states that are indistinguishable to attacker 2. And there's a way in our paper that we combine both attackers, and it's not quite the union and it's not quite the transitive closure. So I'm just going to give you a feel for some examples of how we combine it. So if we look here at state 1 and state 5, if the supervisor sees NA, so the system is actually at state 2, it could be that N happened and attacker 1 inserted the A, or it could be that NAF happened and the attacker 2 deleted the F. So we can see that states 1 and 5 are related because we don't know which attack happened, But if we think we're at 2, it could be the system was at 1 or it was at 5. So in this case, you can see that 5 is in the transitive closure of 1. So 1 goes to 2, 2 goes to 5 in blue. So we could say 1 goes to 5. But on the other hand, we also have that states 2 and 4 are related, and that's not the transitive closure. And the reasoning there is that if the supervisor sees event N, so it thinks the system is in state 1, it could be that NA happened and attacker 1 deleted A, or NB happened and attacker 2 deleted B. So 2 and 4 are related. So we create this relation that comes from the relations of each of them. And as I said, I'm on the screen, I'm just showing it as if it were like the union of everything, but it's not quite the union. And let me show you then, using that relation, how we can see that in this case, an attack can't be prevented. So let's suppose the supervisor thinks the system is in state 2, but as I said, it could be that the system is really in state A and NA has been added. So 0 is related to 2. Then 2 is related to 3 from our relation. And again, the system could have done NAP, but P was deleted. So the problem again is 0 and 3 are not control consistent. So if we check our relation, we would see that 0 is related to 3 according to our relation, and unfortunately 0 and 3 are not control consistent. So an attack can't be prevented. So I'm just gonna, this is close to my end here. I'm just gonna show you here what Michel did next is he implemented an attack on hardware. So some simple RC circuits for temperature control, potentiometer indicating the level of liquid in a, let's say a vat. And at the time that he was doing this, and it was all on simulation and at home, he had some hardware, but because of COVID, he wasn't in a lab. I think he's able to go into it now. So I'm just going to show you a little demo of what can happen if you have an attack on an event. Okay, so if you look here, you have these valves that open up or close, and liquid is poured in here, and we will see in a moment. And as the liquid rises, it rises up. And when it reaches, so if there's no attack, what should happen is when it reaches 90%, you shut the valves, you start a heater and mix the material, and then you release the material through output valves here. What you'll see up here, and is finite state machines that describe the behavior of the system. I won't go through everything. I'll just go through like one of them now. So for example, when I open a valve, then the liquid level gets higher and higher, and it keeps, going through this event transition, and eventually it stops and the valve closes and it returns here. And there are similar finite state machines. I think there was something else I wanted to say about this. Okay, no, I'll just start this. So we imagine that the valves are open, and imagine that there is basically a bad guy who's actually going to mess up the level sensor. So what this bad agent is going to do is it's going to make the system think, or the supervisor think, that the level of liquid is at 90% when it isn't at 90%. So we see here the liquid's rising, but you can see it's only risen about halfway. And because the level sensor has been tampered with, the system thinks that the level is actually at 90% and it's not. So because it thinks that, it's going to now begin the process of shutting off the input valves. No liquid is continuing to pour in. The heater is rising. The mixer is now turned on, it's mixing, and now it's moving the material out. But what it did is it moved material out that was substandard because that material was not at the appropriate level when it was mixed, okay? And you can imagine that this attack, all it did is it produced bad material. An attack that attacked, for example, not a level sensor, but a temperature sensor could cause a much bigger problem, like, an explosion in a chemical plant or some much more disastrous thing than just a bad product. So what remains to be done in the area of security and discrete event systems? So as you've probably already kind of realized, DES models of security fit with cyber physical systems. But, for cyber physical systems, you have, which I know is one of the focuses of your research institute, you have hardware, you have software, you have continuous time systems. So I used to years ago attend hybrid systems conferences, and I found them extremely daunting. And I'm calling this like souped up hybrid systems. So you have all of that, and then you have issues of security. How do we get around the state space explosion that's inherent in most DES problems when there's partial observation? Can we apply discrete event systems to reliable or secure software development? And, incorporating decentralized control has really only barely been touched on. So when I say decentralized control, that can be many things. We could have decentralized attackers. We could have decentralized defenders or supervisors. There are issues endemic to decentralization. So conflicts between different agents could lead to deadlocks or blocking. And some decentralized DES problems are undecidable where their centralized counterparts are not. Some research has been done on discrete event systems on this by Stavros Tripakis, and actually he and I have a talk on decentralized observation at the upcoming American Control Conference. And finally, we really need more tests of real-world attacks to be implemented to get a sense of where our modeling falls short. I really want to thank you for inviting me. I'm really honored to speak here. I list here some people who have contributed to my research on opacity and security. I couldn't do my work alone. And also my students who've helped me with my slides because I'm terrible at making PowerPoint like diagrams and things. Also, this work couldn't have been done without the support of the financial support. So our national funding agency is NSERC, and also the industry funding partners, General Dynamics and Defense Research and Development Canada. And I'm also very grateful to Josh Marshall, who's the principal investigator that invited me to join that project. So I'll just stop my sharing, but I can put them back up. But
yes.
That's it for my talk. I hope I didn't go over time.
Thank you. Thank you very much, Karen. This is a very interesting talk indeed. Are there some questions from the audience? Rob, Serena?
Thank you. Very, very nice talk. Thank you so much. I have two questions. The first is about the necessity of the observer to check opacity. I suppose it is necessary. Is it so?
So do you mean, so I guess, so we're talking when there aren't attacks, but when it's just about opacity. So I guess what you're trying to do there is to make it such that based on the observations of the adversary, they simply don't know whether the system is, so it isn't so much that they do or don't know if it's opaque, it's that you make your system opaque, which means if you are in 12, the adversary doesn't know if you're in 12 or 13. So the adversary's estimates aren't enough for the adversary to know whether you're in a secret state or not. I'm not sure if that answers your question.
Yeah, the other question is about Do you think there is some relationship between opacity and attack detection?
It's a really good question, because in a way, what I presented is two different pieces of work.
Yes, there are different problems, but maybe there is some relation, I suppose.
I think that's a great question, and would be good. Like, so yeah, I don't know. I think that yeah, I've been looking at them separately, and for the papers I see tend to treat them separately, but I agree with you that it should be all part of the same package of making a system secure. So I think that's good research to be done.
Okay, thank you.
Thank you, Elena. Are there some other questions?
So sorry, the question by Elena, Karen, about the necessity of an observer, I couldn't get the answer. I mean, I think the question was, is it necessary to build an observer to check if a system is opaque?
Oh, okay. Sorry. Let me go back to sharing my screen.
Yes, because the condition you're shown, we see the observer.
Yeah.
Okay. I'm just going to try to find I have to figure out how to get my slide. Oops. I'll just try to get the slide I want. So, yeah, okay. So I guess there's two things. There's whether you, okay. Let me, oh, this is slide. Sorry, I'm just trying to figure out how to, I don't know how to do this. See all slides. Okay. Yeah, let's go here. Okay, so let me first say that for the methods of opacity enforcement, all the methods I've seen, and including ours, you build an observer as your first step, which is the exponential growth. So now the other people who've done research in this, so our method builds the observer once, creates this composite structure, and then just keeps paring down this structure. The other procedures tend to build multiple observers, like they build an observer, then once you've controlled it, you build a new observer, then you control it, you build a new observer, which is not computationally great. But I don't know a way around building that observer in the first place. So I'm not sure if that's your question. Is that kind of the first part of what you're saying? Like, it seems,
right, Elena?
Yes.
We are working on the problem of security, and we are really very much interested in what you were saying. So thank you very much. It was very nice presentation. And so we were wondering if you really need to build an observer to check opacity.
Yeah, and let me tell you one other thing, because I don't know if this will relate or not. So before I started working, my main area of research is decentralized control. I'm not really an expert on security. It's in maybe the past 5 years I've started working on this. And so even many years ago, when Jan Willems was alive, we showed that checking co-observability can be done in polynomial time. So co-observability is basically the condition you need to check to see if decentralized control can be done. However, doing decentralized control cannot be done in polynomial time. So we proved that synthesizing a controller can't be done in polynomial time. So not just our method was bad, it's a not I can't remember if it's NP complete or which category, but it's not polynomial time. In other words, it's kind of like you can't seem to get around the idea of building an observer for doing control, but for checking, it can be done. So now getting back to this, actually, I feel like I'm now about to contradict myself, because you'd think that there'd be a way to check. So checking opacity can be done in polynomial time. The problem is, for doing control, you're having to imagine, well, it could go here or here or here, and there's sort of because of the partial observation, there's kind of like a tree-like possibility, and now you have to control all those possibilities. So this is not a proof. My instinct is that, and I don't have very good instinct. So I should say I speculate, but I have terrible instinct that it can't be done in polynomial time. But I would not. I won't swear to that. I only know that in regular, even when there's no security issues, checking observability can be done in polynomial time, creating a partial observer supervisor, which was shown by John Tsiklis, cannot be done in polynomial time. And then Jan Willems and I showed for the decentralized case. Yeah. Yeah.
Okay. Thank you. Are there some other questions? So I have a curiosity, and that I'm asking. So first of all, I'm starting since, let's say, 1 month ago in being interested in this kind of research. Also, Marika and Elena, in fact, Marika and Elena started before myself. It is at least 2 years that they started working this. So I would like to ask you one basic question. What is the information pattern that the attacker has on the plant and the controller in general?
So I guess what different people look at is, like, does the attacker see every event that the supervisor sees? So some people's research, you see the attacker sees exactly what the supervisor sees. Some of them, it sees a different set or a subset.
So my question is, does the attacker has the model, the knowledge of the model of the supervisor and or the plant? Does it or not?
Yeah, so I think it depends on different people's research. So that's where it depends on whether they've assumed, for example, that it's supervisor aware, excuse me, or whether it assumes that it sees everything that the plant generates or not. Like, those are assumptions. Let me get up a slide here that I can show you. Other people, like the other papers, how do I do this? Okay, sorry, I don't know how to do this in a, sorry, I'll just put up, let me find a slide. I have a slide of people who've done research on this. Sorry, I'm trying to figure out how to do this.
Yeah, take your time.
Okay, I can't. Why is this not working? Is this? Can't seem to. Okay, I'm gonna just do this the stupid way because I can't seem to get it to show. Sorry, I did say that I'm really bad at PowerPoint. I think this makes the point sort of disturbingly well. Okay, so sorry, you were saying attack models, right? So first of all, I would look at like, there are people who've done work on opacity and then work on attack models, and I think one of the papers by Alessandro, I think, I don't think I have it on this slide. The one that I have on an earlier slide of Tong et al. I think they have there, they might have a table that compares different.
Okay.
Actually, I'm not sure if they do. We have it in our paper that has not, that's been under review for 2 years. I'll try to find you a paper that summarizes that, but essentially different researchers make different assumptions. So some assume you can see everything that the supervisor sees, some assume you can see, you know, what the plant does, some don't, and how difficult it is to control or not control it is related to those assumptions you make. And I think there's also papers, like for opacity, there's a, I think there's some like survey paper or tutorial paper by Stéphane Lafortune and a couple of other people that was in annual reviews and control. That might be a good place to look for a summary of who's done what on opacity.
Okay. Okay. Yeah, I mean, this is crucial from my point of view, right? No?
Yeah.
When you're studying security, right?
Yeah, totally.
And also you were mentioning this issue about cyber physical systems. Here at DUS, we are working since many years on this, mostly on control with these logic specifications. And indeed, it would be great to mix, the stuff on discrete-event systems with differential equations. In fact, with Mark and Elena, and this is one of our next goals. In fact, with Marika and Elena, we already worked with these notions of diagnosability and predictability applied to differential equation. It would be great indeed, to extend this kind of research, to more complex systems.
Yeah, it's very hard. Like I find hybrid systems very hard. Yeah, it's really hard.
It is a challenge. Yeah. Indeed.
I want to mention, just as an aside, that Patricia is giving a talk tomorrow. I don't know if you're all familiar with the Discrete-Event Systems Lightning Tutorial Series, but it's IEEE tutorials. You can sign up for it. It's all remote, and it's on different topics of discrete event systems. Because I know they've had ones in the past, I think, on you were mentioning diagnosability, and I can find that email and send it to you. If it interests you.
Yeah, that would be great indeed. Thank you very much. Okay, so are there some more questions? Oh, Naime. Yeah, we have Naime. Please, Naime.
Hi everybody. Can you hear me?
Yes.
Okay, great. Just I wanted to thank you a lot because of this interesting presentation. It's completely aligned with my research interests and what we're doing with Professor Di Benedetto and Professor De Santis. Just I have a question that how you model the attack. I mean that you just consider it as a function of events, or no, you just model it with another, discrete event system, or how? Because I wanted to know that how you model with a consecutive attack happens, but with different behavior. I mean, the first time is going to, for example, replace A with something else. The second time something else. Just I want to know how you model this kind of attacks. Thank you.
Yeah, so so for the work we did, we were really only looking at, again, one attacker at once. So, and that's the work also of Wakeki. We started looking at, but are just kind of in the middle of it, what if you have multiple attackers and those relations you have to create become much more complicated. So in our case, we're imagining that so in our case, it's just like a mapping that deletes or inserts certain events. I guess, yeah, I think I understand your question. You could represent it with a finite state machine that captures the altered structure. I'm feeling stuck on answering that properly. I think I'm not answering that properly. Do you want to elaborate a bit on what you mean? Maybe I'm kind of getting it wrong. Or let me say, I think if you had multiple attacks, you can compose, like you'd have a composition of things. But as I said, we were looking at, there's just one attacker attacks. You just don't know which one.
Okay, great. Thank you for your information. Again, thank you for your interest.
Thank you.
Thank you.
Thank you.
So Karen, one attacker is going to of a string, right, of symbols, where you are. I think you were erasing one and inserting another one.
Yeah.
So this is one behavior of one attacker.
Oh, yeah. So,
but it could also do things, right? Could also,
I'm sorry, I lost you. It cut out. Sorry.
so the attacker could also replace another symbol than the one you were showing. I mean,
yeah. So in some sense, deleting and inserting is kind of like replacing, because you could
Right.
delete that and put something else is effectively replacing it. Yeah.
So, but we are modeling which symbols could be replaced.
Oh, so yeah, so we assume, and again, this is just taken from Wakeiki's work, that you're given like what symbols each attacker is allowed to attack. So if you had, 5 attackers, you're saying attacker 1 can attack, symbols ABC, attackers 2 can attack symbols AFO. So that would be part of the problem setup, is you are told what symbols can be attacked by which attackers. And they may or may not have overlap or whatever.
Thank you.
And then, so step by step, the attacker can attack as they want. At any time, at any step, it is possible to have only an attacker on, but at any step, any attacker can be on.
Yeah, and actually, that's kind of leading to more recent work that Michelle and Patricia and I are doing, which is looking at, so this, what I showed you here, was there's sensor output, and that's altered. But we're also looking through like a real implementation at what happens when an attacker's at different spots in the system. Because if it's in a large system and there's a network, then if it attacks what goes from the network from one agent to another, if it attacks what's coming out of an actuator, what's coming out of sensor. So we're just in the, like at the beginning stages of that work, of trying to understand how to model what's going on if you have different positions for the attacker. I don't know if that answered your question.
So you said you have a paper at CDC on this topic you were presenting?
Well, the one on the attacker one appeared in Journal of Discrete-Event Dynamic Systems. Mm-hmm. The one on degree of opacity we submitted.
Okay.
Although I don't know. I don't
for your papers.
I can't swear to you it's going to appear. It's just I don't know. But
yeah.
And then the one on that process of how to enforce opacity, we submitted to a journal, and it's been in review for like 2 years. So, and it was accepted subject to minor revisions, at least I want to say like a year ago. So we've been like, we revise it, and then we get back, oh, and also this, and then we revise it, and so it's been 2 years. So unfortunately, that's not yet. I can't remember if we've put it on archive yet or not. I can search, but I really, really hope it just appears soon. But
okay.
Yeah.
Thank you so much.
Thank you.
Okay.
So these papers are not available yet, right? I mean, they are not available on archive. The paper.
Yeah, so I can send you the paper. Some of it is on archive. So the one with Michelle and Patricia that appeared in JDEDS, and I'll look for the other ones and send it to you. I'm just writing down your email, or I can send it to you,
Giordano. I think it's fine.
Sure. You can send to myself, and then I can forward.
Okay, I will. I'll happily do that.
Thank you very much.
Thank you.
Thank you.
Okay, thank you very much, Karen. Are there some more comments?
It went late. I'm sorry it went late for your time.
No, that's great. That's great. Definitely great. Okay, so thanks again for being with us today, Karen.
Thank you. I appreciate it.
Wish all of you a good afternoon, and goodbye.
Thank you, Giordano.
Thank you. Bye-bye.
Goodbye, Karen.
Bye.
Goodbye.
Bye.
Good afternoon.
Bye-bye.
Bye. Thank you.
Goodbye.
Goodbye. Thank you.